is a very shameless refresh of a presentation I gave, I think, a couple of years ago. And it's to try and give you a view of the main patterns we have in the code and the main good practices we try to instill on people by force. And it's not going to give you an A to Z overview of the code, but hopefully it will give you a good enough description of the SU2 structure to make it look less daunting, and it should also give you plenty of resources for many other things. So, for example, for an introduction, we have everything written up on the website for how to get started with the development, how to get started with GitHub and so on. And there are talks from conferences way back that will, put the same process in kind of a presentation format. Okay, so the main important thing for me as we develop code is to do kind of a continuous cleanup approach. So don't try to over predict what's going to happen, what's coming next, and spend too much time trying to generalize things. But as you put in a new feature, learn with what's already there, and quickly refactor things if you have to at that point. So we try not to duplicate anything in SU2. So don't copy paste and then modify things. If you are in a situation where you need to do something that looks similar to something that's already there, cut and paste it to somewhere else, and then specialize those things. And I'll give you some examples of what specializing looks like. And that's especially important with logic. So if you have repeated logic in your code, I can guarantee that you have bugs, or that you will have bugs, because it's very difficult to keep this type of things in sync across the entire code. So you'll also see that we try to abstract away the type of logic of is an Euler problem, is a viscous problem, is a Nemo problem. Try to abstract that away into just one function that potentially inside does compares different types. Then we also try to promote good abstractions, or abstractions that are inherently reusable in other areas. So for example, math is better than domain-specific things. For example, dot product is a better abstraction than normal velocity. They do the same thing, but if you see, you're not going to be inclined to reuse something called normal velocity somewhere where you are dealing with geometry and not with flow quantities, for example. So you can still call your variable normal velocity. That's good variable naming, but the function is a dot product. And then generic code, and again references. And that means algorithms that do not depend on specific data structures, and that means that interfaces of the type IJ are better than kind of manually hard-coded memory layouts for 2D indices in a 1D array, and that's even better than kind of vector of vector or a pointer of pointer to represent a matrix in this case. So try to write code against interfaces and not against hard-coded assumptions on the layout of things. Then general good programming practices. So trying to use all the language features we can to write safer code. Yeah.
I didn't get what you mean by abstractions where this IJ. What's that abstraction?
Okay, so say that you have a type for a matrix, and you want to access row I, column J of that matrix. So the underlying storage of all the data of the matrix is usually just a single array, just a 1D thing. Well, everything on a computer is pretty much just a 1D thing. And so then you have two options for how to, well, you have some options of how you, of what you do with the 1D array to then get to a 2D indexing space, right? The row major, column major, something more exotical. So regardless of that, the matrix type just gives you the operator ij. And then internally, you have the details of how things are stored in memory. So it's just abstractions in the sense that the implementation detail, in this case, the detail of the storage layout, is encapsulated inside the type, right? So it's okay. So language features to write safer code, and that's const correctness, making everything as you can const, reducing the scope of your variables, because if you have some very long function, at some point you don't know what you're modifying anymore. In our case, so with the virtual classes we have, also virtual qualifiers. So saying that a certain function overrides a virtual method, and then you know that this thing is actually overriding a function and not just shadowing that function. And preferring small functions and classes with very explicit interfaces. So trying to minimize the hidden state that we have in SU2, which is kind of also one of the major sources of bugs, because usually the patterns we have is that we have a class, and that class has some internal state, and then you call some function, and that function does some operations and ends up modifying that internal state. And then it's very hard to guarantee that if you call the same function again, it may not give you the same result, or there is room for that function to not give you the same result because of the hidden state every time that you call that function. So that's something you avoid, or that you manage, by having small functions, and a function cannot have state. Well, it can, but it shouldn't have state. And small classes are usually also easier to manage. So a good example of this, for if some of you know SU2, is that we have this numerics classes, and we cache a lot of things inside the numerics classes. There's all this storage for velocity and for intermediate computations of the fluxes that are being computed, for example. So having all that state is generally not good. Yeah, and there's plenty of references of the things I'm mentioning here. Okay, the other pattern, and this goes towards both having more kind of math abstractions instead of physics specific, and having less state in classes, and kind of free functions that can be applied to different things. Other things you see in the code is things like this. So a function to compute gradients, green Gauss. And this thing operates on field, any type of field, as long as it gives you this kind of interface. So as long as this type gives you this interface, it will work with this function. So a while back in SU2, we used to have compute solution gradients to compute the gradients of the solution variables, and we used to have compute primitive gradients. So that, in a sense, is not the ideal abstraction. It's okay to start with compute solution gradients, but as soon as you need the primitive gradients, now you should refactor things out and just, okay, compute gradients, and it operates on any field, and the field in this sense is just a 2D matrix and or a 2D array, and it outputs a gradient type, and that is just a 3D array. So again, math abstractions. There's complexities because of communicating quantities, but just because we cannot have everything doesn't mean we should have nothing. Okay, then the next, on a similar topic of having generic functions for certain types of methods or numerics, we can also have generic classes. And so the example of the solver and what we try to do with a number of classes is that you have some base class, in, for example, C solver or C driver, C iteration, C whatever in SU2. And this is supposed to just give you an abstract interface for general operations. So what are the actions of a solver? The actions of the solver can be pre-process, post-process, iterate, whatever, generic things that the solver can do. It shouldn't be very physics specific things like I don't know, get drag coefficient or get lift, whatever. So that's kind of polluting the interface of something that should be generic. Then in the middle, as we go to Euler solver and C and the Navier-Stokes solver or RAM solver, we have some base class for FVM flow solvers, right? And so what this allows is that here you can have an implementation of common methods. So there's a lot of things in common between computing for example, the time step for the Euler solver and the Navier-Stokes solver. Or there's a lot of things between computing the time step for the compressible and incompressible solvers. So we can have generic implementations of those methods, and then allow the derived classes to instantiate those methods or those functions, with the implementation details. So we have this kind of pattern allows the derived classes to specialize generic implementations. So for example, we have this center dissipation sensor, and this is done by the generic solver or by the base solver. And one of the things that this accepts is a functor, and this functor returns the center variable. So the way to compute the sensor is the same, but the sensor variable is different for different solvers in this example. And so the derived solver can now define a little object with an interface that is common across all the derived solvers, and it returns the sensor variable, which in the case of the Euler solver is pressure. And sometimes the thing it may not be the variable that's different. It may just be the way to access the variable. So here we're getting the variable from the nodes of the solver, or the C variable class, if you know. But you can maybe have that variable in a different place. So imagine that you want to compute this kind of sensor, but for a turbulence variable, or for even for some intermediate quantity that you computed on the fly and you want to compute a sensor based on that quantity, then you can use this type of pattern to return that new variable, that sensor variable, and then instantiate the generic implementation with that kind of information. So this is the same thing when you do STUD sort, and you can put in a custom comparison operation for the types that you're sorting. It's the same kind of design pattern. Okay, so other families with a lot of intermediate classes to reuse code. It's well, a good example is the output, where you have there's a lot of levels in some sense, but this does allow you to not copy paste a lot of things between these four classes, for example. So from the general output that just defines the interface to set a history variable, get an history variable, write the history. You then have something that encapsulates all the outputs that are common for FVM solvers. You have, of the FVM class, you have the heat solver and the flow solver, or the flow solvers. So there's a lot of common flow variables across these things. So they all have velocity, for example. And then you have the specialized things for compressible, incompressible, NEMO, which has other outputs for temperature and for the different mass fractions of the gas components, and the high order solver. And here the main difference is not just the type of variables, is also to some extent how those variables are accessed. So, okay, and yeah, this comes from Doxygen, which is probably the best way we have to explore these families of classes, and maybe we'll go into that later as well. Then another good kind of practice we have is try to make it simpler to write code and kind of reduce the boilerplate. So for example, if you introduce some new configuration option that has a number of parameters, you could be inclined to add a bunch of methods to the configuration to get each of those variables. But usually all those things are used together. You need the parameters for a boundary condition. You're going to use them all in your boundary condition, usually, or you're going to use them all in your turbulence model. So what you can do to make things simpler is that just package all those things in a little struct or whatever. It's just a dumb custom piece of data in some sense, and then you just get the parameters for each feature. And it's just one function instead of all this stuff that you have to document and so on. Yeah, and so making types is a completely natural thing in C++. So just make types. All right. So where do you put things in the SU2 structure? So we have kind of this hierarchy of not the importance, but size maybe, or abstraction. There's the driver level that kind of has the structure of advancing one time step, for example. You have the iteration level, which has the kind of abstraction of advancing a fluid iteration versus a structural iteration. You have integration, so spatial and temporal integration, and here single grid versus, you can think single grid versus multi-grid, for example. Then you have solver level, which encapsulates kind of physics, heat transfer, fluid flow, structural mechanics. And from there, you have the details of how you discretize the equations for those physics, and that's kind of your numerics classes and so on. So if you have a new function, where do you put it? Where does it go? So it should go into the rightmost abstract operation you can. So you don't want to put a small kind of operation in the driver, right? The driver doesn't care, shouldn't care about computing source terms. And you should try to fit it in one of the existing generic hooks. So like if you have something that qualifies as the solver pre-processing, that's where it should go. If you have something that qualifies as the spatial integration, that's where it should go. And then within each hierarchy of these things, so within each hierarchy of solvers or each hierarchy of numerics, you should try to put it to the left. So at the level where the most people benefit from your new implementation or your new whatever, right? So if there's a new output, if you want to output a new flow quantity that's relevant for all these things, then put it here. Don't put it here just because you're doing compressible flows right now. Okay, so what's the importance of this? What's the importance of putting things in the right place? You want to make sure that your operation occurs at the right time, right? So we have this high-level things that don't know anything about the solver and the numerics and so on, and these are calling generic operations, kind of in a dumb way, trusting that this is doing the right thing, right? So that this thing knows what it means to pre-process whatever physics. So you want to make sure that the operation you're putting in occurs at the right time, so that you're not lagging things, for example. You don't want to put something in the post-processing and then it doesn't. Then it's like one iteration behind because it should have been way before. Yeah, and also because other developers may not know where to call something that they never seen before, or they may not know how to call it. So what are the prerequisites for that function to be called? An example of that is that you need to compute the limiters after you compute the gradients. Yeah, so by putting things at the right level of abstraction and trying to fit it into the existing interface, not making that interface harder to manage, you make sure that it's more manageable for everyone else to do this. Okay, so practical development aspects. Get on our Slack channel and try to find out who's working on whatever feature, so that maybe there's some cooperation, or maybe there's some lessons to be learned, or maybe someone tried to do something already and they have some work that they left behind, and maybe you can pick that up. Weekly developer meetings, see Slack for the schedule. Use GitHub issues, discussions, draft pull requests to document the development and document the issues that you're facing. From time to time, I've found it useful to see how the code is being used out there. CFD Online, it's actually a pretty good resource for that. Yeah, there's a lot of questions on why MPI doesn't work for me, but from time to time you do find a bug in the code because of a problem that someone's having, and it may be your code that they're struggling with. And yeah, there's a lot of smart people in this community, so definitely take advantage of that and interact with others. Um, okay, so other things, start from a good reference. So the same thing as you do with your research, you don't get like you probably don't get a paper. Well, you start reading papers with the ones that have more references, probably. Right? You don't start trying to base your research out of something with one reference, one citation, sorry, and it was written in 1865. You probably don't do that. So look or ask where to find a good reference inside SU2 for something that you may be trying to implement. So looking for kind of the state of the art or the most modern implementation of something. And if you are new to C++, definitely invest some time in learning best practices and so on. So like, if you're doing something with MATLAB or whatever, you'll probably pick up some tutorials for MATLAB. And so C++ is not any different from that. So, well, it is because it's a bit more complicated, but you can get surprisingly far with very few guidelines in writing efficient code and kind of understanding the spirit of the thing in some sense. And I have a chapter on that because I spent too much time writing code in my PhD. And yeah, finally, use GitHub effectively. Advertise, discuss, design things before you go into some big project. I mean, that's my advice. Some people, others have other views on this, but open draft pull request and try to find collaborators. It's a bit frustrating that in 2023, where everyone knows about everyone's life, it's still like the 1800s, and people are still discovering things independently. Divide work in packets to kind of facilitate the integration into the code and also the code reviews. Oops. And what, there's something, yeah, try to separate your pull requests into, yeah, I mean, I understand that usually the development process is you're trying to do a certain application and you stumble on a bunch of things and you end up fixing up different things, right? But especially if they're fixes, try to put them as soon as you can into the main version of the code. Add unit tests for your code. And it's actually a good practice to do that at the start, not after you finish writing the code, but it's good to, what what you expect your code to do. So you can kind of design the test before you start writing the code. And then the code starts meeting your tests as you go. So that makes it a lot easier to, it seems like a lot of work, but it makes it a lot easier to, you don't want to write 5,000 lines of code and then you start testing those 5,000 lines of code, and that makes it a lot harder for you to find problems. Yeah, definitely come and review some PRs, and also, to make GitHub better for everyone, don't kind of pretty format the code for no reason, like deleting a line here and there and putting a line here because you can read it better that way. We have an auto format thing, which is still not applied to all files because we're trying to be nice to people. Yeah, and check out what's going on with the develop branch at least once a week, and see what's new, and that's it. So for the, I don't know how much time. Okay, I don't have any time. Damn. Well, we started late. So what I was thinking now is to open up for questions and suggestions of what you may want to see. So what would be beneficial for you in terms of, you want me to talk more about where you can find documentation, test cases, or more about the code structure, more about the development tools that may help you, more about the algorithms or schemes that we have in the code. So I don't know, what do you think? one of the, yeah.
How do you like to develop in terms of IDEs, environments? What do you like to do?
I mean, it's whatever you're familiar with. If you're starting now, I think Visual Studio Code is probably the best thing out there. Another thing I was thinking for this would be to, yesterday we got the feedback that it's, as when you get into the code, it's daunting to look at. So I thought I could show you how to try and use Visual Studio to navigate the code and kind of, get past the. Is that a good idea? I see some nods. Okay, let's do that.
Pedro, we beat that one really, but the law what you said is very some examples with that. For instance, the idea of testing small pieces of code that might be.
Can try. This is not going to be very nice for the people online, but yeah, but Linux and go to webinar do not work very well. Sorry. So I can't really share the screen with the people online, I think. Can we duplicate the screen? All right. Okay. So can everyone see that? Okay. So where does the code start? The code you execute is called SU2 CFD, and so the file is SU2 CFD.cpp, and it has a main function. Promising stuff. So what happens here? A bunch of configurations options, blah blah blah, weird API stuff. So try not to miss the forest for the trees. Main SU2 driver. That sounds promising. So there is a driver. Now you know something else about the code. There's a config. The code is actually kind of well documented to some extent. A driver is created, blah, 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 blah. Nothing happens yet. We're just, instantiating the driver. And then eventually start solver finalize. And you're done. That's, you're pretty much done at that point. So start solver, what happens in start solver? So let's try to use Visual Studio Code to see what happens here. Start solver and you land on a virtual method. So because it's virtual, you already know, okay, there's some other class, not this one, because this one is not doing anything. There's some other class that defines what start solver means. So let's see if Visual Studio is kind to us. It is. So this is telling you all the things that have a start solver, right? And it's also giving you the uses of start solver. So if you consider, for example, single zone driver, we can navigate to that. And then we can control and click that again, and we go to the start solver of single zone driver. So we are already, with a few clicks, doing something interesting with the code, or looking at where the magic starts to happen. So we go in, okay, you have a loop over time iterations, and now you have a bunch of actions that constitute the time iteration. So pre-process, run, post-process, state, monitor, output, and that's it. That's what start solver does. This is what SU2 does at the visit file. So run sounds like the more promising one. So let's see what that means for a single zone problem. Run. Run calls something that's in the iteration container, and it's a C iteration. It's of type C iteration, and it does solve. Okay, so it solves a time iteration, or it solves an entire steady problem. So you just keep going with this. Solve, control, and click. And, let's see where you land. And you land again on a virtual thing that doesn't do anything. So already you know that there are other iteration classes that that actually implement what solve means for that type of iteration. And go again. And you just repeat the process. So what kind of iterations do you have? There's a FEA iteration, there's a fluid iteration, there's a, yeah, the main one, I guess you'd be interested would be fluid iteration. So we can go and jump to that. Double click. And we already have a few files open. So what does it mean to solve a fluid iteration? So what happens here? Preprocessed, so there's kind of these generic things, preprocessed solver, and then we go into the inner iterations. So either inner iterations of a time step or the pseudo time iterations of a steady problem. And so what we're doing there is just iterate, monitor, output, repeat. So the important thing that happens here is just iterating the solver. This is just iterating the solver. So let's go, fluid iteration, iterate. So what we do here, multi-grid iteration, and then we do all the little, all the other models. So transition, turbulence, there's going to be the heat solver here, doing its own iteration as well, radiation solver, and so on. Okay. So I think that gives you kind of an idea of the process. It's too complicated. I mean, there's levels, but you can peel the onion relatively quickly. So, multi-grid. So I'll try to go until the point where we actually see what a solver starts to.
Sorry.
Yeah, okay. Well, at some point, you get the problem that that Visual Studio stops following the trail of breadcrumbs. So yeah, now you have the poor man's approach. Gotta break my neck. Come on. Oops. So when everything else fails, when the clicking fails, you can just look for things. And when you're at the high enough level, there's actually not that many places calling that thing, right? That's also kind of the benefit or kind of the intention of having this kind of hierarchy of classes, is that it's a kind of a tree. So once you're close to the top, everything is still relatively narrow and easy to understand. So where's the definition of this? Here. The multi-grid, the multi-grid is complicated on its own. So but anyway, you get to the interesting parts. You have space integration and time integration. So let's see what space integration does. So now you're finally starting to call solver things, and you're computing centered residual, or upwind residual, viscous residual, source residual. So, and then you're applying boundary conditions. So relatively quickly, you already got to the points that call the solver, and then depending on what you're interested in seeing more, you just keep going. Center residual, it's again an abstract thing that the solver may do, but you can continue to untangle it like this. Yeah. I don't know. Is this does this make sense? Does this make is this new? Does it make your life easier? I don't know.
Useful stuff. People interested.
Yeah, Toby.
Yeah, I would say that. More work to do with the function, it can be a little overwhelming, like with the, you see that, you need to go to the most iteration of what is the default or the right forward. What I usually recommend is to get familiar with flexible VSO. I think it's pretty straightforward. Because then, especially with the class hierarchy, you can step through the code, as to you're not relying on you finding stuff. You can just advance the code line by line, and it will automatically, of course, then step in the class instantiations that are actually called. So you're never guessing, am I stepping down this function like this? Because we have an factory for instantiation. So when, for example, when you're not exactly sure how to implement the row scheme or JSP, then if you just start, for example, the integration scheme, this is what most people are familiar with. The digital environment. And so there, you see where you're coming from. So you see, okay, I'm coming from this time loop or whatever. You can click up, and you can also step down and you know exactly where you're going. So instead of, it's very cool to be able to find stuff by searching and these interactive things. But if you are a little bit unsure, you just go into the environment and step through and see what is actually happening. So that's what I did a lot, especially with AD, because I didn't know what was going on and had some false assumptions. And suddenly when I was going through the code, I was thinking, okay, why are you doing this or that? And you create this, that's what's happening and it works. So then you can try to deduce why it works. So debugging, in my opinion, is really these debugging tools are really what is super valuable.
And then why did I think I'm going those? Because it's so complicated that you can't memorize it.
Yeah.
Oh yeah, I mean when I first get to a code, I mean I'm going through this process, but I'm going through this process, the 100 miles an hour. But when I do this for the first time for a code, and that's how I started with SU2 as well, you note down the levels where you are, right? You start all this kind of script that we've been taking from the main function to the driver to the things. Then, yeah.
Okay. So that's it.
Yeah, because I've been, everything was closed and I've been opening one by one. But you note down what are the different, what are the main things that each class does and so on. And then the other good resource that I want to point people to is just Oxygen, which is very easy to build. I mean, you just open your command line, and if you installed Oxygen and all the stuff, and just run Oxygen here, and then it goes into .html, index.html. That's kind of the main page for the documentation, and we have it organized kind of in topics like this. So depending on the things you want to do, this is how you can know what classes to look for in the code for a particular thing. So scalar transfer. you have the solvers that are related to scalar transport, and you can go there and you see how these solvers relate with other ones, right? So here, scalar solver happens to be one of those generic ones that I was mentioning, and then from there we get a turbulence solver, we get a species solver, and we get a heat solver, and from a species solver we have a flamelet solver, and from a turbulence solver we have the different models, SA, SST, and the transition solver is also coming from there. Yeah, and you see what functions the solver has. So it's pretty useful, and you can use this to jump to see how the classes relate to particular physics things like turbulence or Navier-Stokes Euler, how the viscous or source terms are computed. Yeah. Okay. Yeah.
So a lot of these diagrams seem very hard to purple. I'm just curious if there's any like high level
High level what, sorry?
flow charts, data flow, kind of like how you step through like this thing, communicates with that class, and all that. It's kind of showing a very high level of data flow.
No, we don't have. Yeah, that's not something so easy to generate.
You probably do like a trace, I guess. That would be helpful, I guess, of documentation.
Okay.
For like beginners.
Yeah, cool. Right. My time is up.
Thank you.